For our CS4243 project this semester, we are implementing a dice recognizer, and our team consists of me, Sigmund, and my teammate Johannes. So let's start with our project motivation and description. First of all, we realized that this is less of a data science problem, but we figured that this will be a more fun and practical way to use AI in our daily activities. As you know, many tabletop games use dice as their real-world equivalent of a random number generator, and there might be some use case to read the results of these dice rolls into a computer quickly and accurately. As for the description of what it will just be an implementation of MLP, CNN, and faster RCNN using the dataset of our various dice rolls. As for our data acquisition, we figured it will be faster to gather data using our own controlled datasets. So we took many photos, both for individual and multiple dice with varied positions and rotations for the network to learn.
Next, we are going to discuss about our deep learning solutions. We have MLP and CNN for individual dice and faster RCNN for both individual and multiple dice. Firstly, we tried using MLP with 3 layers to see its performance. We modified it slightly to adjust to the image size input, and we tweak the learning rates, and finally use a library to import the images from our local folders. Even with all of this algorithm is still unable to correctly identify.
And then we tried a CNN implementation by using the VGG network. We modified it slightly to adjust to the image size that we have, and we also tweaked the learning range, and finally use a library to import the images from our local folders to the PyTorch tensors. With all of that, the results of this network is highly accurate, especially when compared to the previous MLP implementation.
The dice, because when training, it still produces error. We tried many things. We tried tweaking the learning rate and stuff. Next, we are going to discuss about our method in faster RCNN, especially for individual dice. Before we take images into the faster RCNN, we made the labels and the bounding for boxes with the help of label image, a software for labeling we found on internet. In this faster RCNN, we only wanted to identify the pips or the dots on the dice top surface. Hence, we need only the model for one class, which is in this case, the dot. So I decided to use a very low approach of developing further on our Lab 11 code. To suit our needs. First, the inputs. I added support for manually labeled images from the XML file with a variable number of dice. This is in contrast to the Lab 11, where the data is data labels. Data labels are conveniently generated. Second, for the network, I added support for the network. I added support for variable. For the network, I added support of a variable number of prediction outputs. For this to work, firstly, I had changed the lab. Second, for the network, I added support of a variable number of prediction outputs. For this to work, I changed Lab 11 method of picking up top and anchors, and instead of extracting anchors that passes a certain threshold, then I implemented the non-maximum suppression using PyTorch. But after implementing and running it, these are the following issues we encounter. There are a lot of boxes still highly overlapped, which is too many of predictions that we deem undesirable. It's a bit hard to see on the image on the right with many overlapping boxes, but we deem it knows where the pip is, and thus we think this could work. But it needs more improvement. So in the future, as we saw the problems in the previous slide, the future improvement I think is necessary for the accurate counting of the pips or the dot. In this case, 1. We can use intersection to find out how many. Another is to develop clustering and use that clustering to find how many the pips are. So next, we'll be explaining faster RCNN for multiple dice.
And finally, we get into recognizing multiple dice inputs using faster RCNN. As mentioned before, we manually capture our photos, and for multiple dice, I then manually label over 500 dice for the dataset. And as for the implementation, I decided to use a low-level approach by developing further on Lab 11's code to suit our needs. First, for our inputs, I had to add support for manually labeled images from an XML file with a variable number of dice. This is in contrast to Lab 11, where the data and labels are already generated. Second, for our network, I added support for a variable number of prediction outputs. For this to work, I first had to change Lab 11's method of picking the top n into top n anchors, and instead extract anchors that pass over a certain threshold. I then implemented a non-maximum suppression using PyTorch's operations library. Finally, I considered adding region proposals for different bounding box sizes, but I felt that it was out of scope of this project, as the dice tend to come in the same sizes anyways. But after implementing and running this network, I came into these following issues. First, there are some false negatives and some other bounding boxes that are overlapping. I figured that in the future, it can be fixed with a better NMS filter. And then, there are many classes that are still not predicted correctly. So on the left here, it's a bit hard to see, but only about half of the anchors are predicted with the correct side of dice. I feel like this can be helped a bit with better and longer training and by adjusting the learning rates and such. Finally, there are some issues with multiple dice faces showing at an angle. So in the bottom left corner there, you can see a dice where two sides are facing the camera and it moves the counting box a bit up. This might cause some issue in the prediction, and I feel like we need more training data for these fringe cases. And for the future developments of this neural network, first, after fixing the issues mentioned beforehand, we will have to account for different angles, lighting, and background, and account for different dice types, which are usually used for different games. And finally, implement real-time video detection for practicality in table games. And that's all we have for our presentation. For our practical game use, we think that we should further develop on the faster RCNN side for multiple dice. Then, we should also add a way more diverse dataset before this can be considered practical for real game use. And finally, we also thought of extending this neural network classification with practical features for table play, such as dice roll history and displaying the total number that is rolled. And that is all that we have, and thank you.